Yeah, good morning to all of you. So today we are going to discuss some nice concept. So RS codes, but you no need to worry about what is coding theory and all. Okay, we'll go very systematically. So first of all, let I am denoting AN. Let AN is equal to, right? So let AN is equal to. So I'm constructing n by n matrix. Okay. So look at this. So first column is 1, 1 like that up to 1. Okay. So second column is that x1, x2 and so on, xn. Okay. Third column is x1 square, x2 square and so on, xn square. Okay. So can you somebody tell me what is the last column? So I told that the size of this matrix is n cross n. Can you tell me the last column?
x1 to the power n minus 1.
Yeah, x1 power n minus 1 and x2 power n minus 1 and so on, xn power n minus 1, right? Okay, here you may be wondering that what are these x1, x2, xn, correct? So what we'll do is that let fq be a finite field. Yeah, let fq be a finite field. So finite field with n elements. Sorry, with q elements. You know that the finite field fq means actually finite field with q elements, right? So that implies what? So basically this q is of the prime power n, right? This implies fq has a characteristic has a prime characteristic say p. In that case, then this my q is equal to some p power l, right? So q is of the form prime power. Every finite field is of order p power l. Okay, don't worry. So these are not. I told you that today completely easy hoga, but yeah, but just assume that finite fields order of a finite field is always prime power. That we proved, but if not recall, then just remember that. Okay, what is that we are doing? These x1, x2, x1 comma x2 comma and so on comma xn. These are elements in fq. So usually distinct elements. If they are distinct, then what we can say about n and q? If they are distinct, yeah, it is clear that n is less than or equal to q, correct? Yeah, okay, fine. So I'm constructed a matrix an like this. Okay, so somebody can tell me what is a1? Yeah, can you tell me what is a1? Not a1, a2. Yeah, so can somebody tell me what is a2? See, an is this, right? First column is 1, 1, 1. Second column is x1, x2, xn. Third column is x1 square, x2 square, and so on, xn square. Nth column is like this, right? Nth column is x1 power n minus 1, correct? Yeah. Can somebody tell me what is a2?
1x1, 1x2.
1 x1. First column is 1, 1, and the second column is x1, x2. So I hope a3. One more time. Okay, sorry for this. So one more time. Somebody.
1x1, x2, x3, x1 square, x2 square, x3 square.
Yeah, x2 square, x3 square. Okay, so clear, right? Yeah. So now I'm now this is okay. Now I'm constructing something. Okay, that is called. I'm denoting it as x1 d, d of as a function, comma xn. Okay, which is equal to determinant of an. Okay, nothing actually. I can say determinant of an, but I'm calling it as a function, right? Okay, so my goal is to find out this value. Okay, goal is to find So you may be already come across this, right? It is called Vandermode matrix, and determinant also you know. Goal is to find d of x1 comma. Oh, it is, there is a problem happened to this one. Okay. So let me open again. Yeah, restore file. Yeah, okay. So let me save it. Yeah, give me 1 minute. So some clap, it board is crashed actually. Okay. Right. Yeah. So are you able to see?
Yes.
Yeah. Okay. So right. Yeah. So start thinking about that. What we can do about the determinant, right? So think about the determinant, at least A2 and all you can figure out already, right? So goal is to find the determinant of these matrices. Okay. So that part is clear to you, but yeah, how do we do that? Okay. So yeah, okay. So this my question is that what is the find d of x1 next to xn, right? Yeah, right. So I hope it is very clear to you that what is d of x1 next to, right? What is d of x1 comma x2? This is equal to determinant of 1 1 x1 x2. Can you tell me?
x2 minus x1.
It is x2 minus x1, very much clear. Now let us compute this x1 comma x2 comma x3, right? Before that, you can also tell that if you know the answer, okay? We'll verify, okay? Yeah, anyone of you know the answer? These will come in the while Lagrange interpolation techniques and all, right? Yeah, but in here, so is it anyone of you know the answer? Okay, no problem. So let us derive it. What is it we do now? So we do the column row operations, right? So I'll keep one first row as it is, right? Second row I will do it R1 R2 minus R1, right? So x2 minus x1, yeah. So and x2 square minus x1 square 0, x3 minus x1, x3 square minus x1 square, right? Yeah. So can somebody tell me now what is next step? So from the second row, what I can take common? X2 minus x1. Okay. And the third row, I can take x3 minus x1. Right. So now the matrix now becomes, so 1, x1, x1 square, 0. Right. So here 1, 0. And this one becomes x2 plus x1. Right. And this is x3 plus x1. Okay. Yeah. But now again, you know that determinant we can expand along the first column. So it is x2 minus x1 into x3 minus x1 into, so determinant of this portion, right? I am writing one more time. So x1 plus x2, x1 plus x3. Yeah. So what is the final answer? Yeah. Can you tell me? x2 minus x1 into x3 minus x1 into, yes, one of you.
x1 plus x3 minus x1 plus
Yeah, final answer कितना होगा? Final
Oh.
answer.
x3 minus x2.
x3 minus x2. So are you able to see some sort of can you predict the formula now? So d of x1 x2 is x2 minus x1. D of x1 x2 x3 is x3 minus x1 x3 minus x2 x3 minus x2 minus x1. You see that? Yeah. So what is the conjecture? What do you expect that d of x1 comma x2 comma and so on xn? What is that you expect? Yes. Yeah, Kanak, can you tell me?
Phi.
Sir, xn minus
Product.
xn minus xn minus 1 all the way up to x1.
Okay, so tell me direct product. Okay, I is equal to 1 to n, j also equal to 1 to n, right?
Sir, so it's I plus 1.
No, not like that. See, can you tell me what is a d x1 x2 x3 x4?
It will be x4 minus x3, x4 minus x2 all the way up to x4 minus x1.
Right, like that, right? So how they look like? So xj minus xi, right?
Yes,
What is the relation between j and I?
the conjugated.
It's conjugate to x3 minus x1 is also there here.
J is greater than I.
J is greater than I, right? You yourself told x4 minus x1, x4 minus x2, x4 minus x3, right? Then x3 minus x1, x3 minus x2, then x2 minus x1, right? So it is all xj minus xi where j greater than I, both I and j from 1 to n, but this is the condition. Okay, so we try to prove that now. Okay, we are trying to prove this part, whatever we told till now. Okay, so we prove the result by induction. Okay, we prove the result by induction on n. Okay, so n is equal to 2, you already checked the result is true, right? N is equal to 2, the result is true. Right? So now suppose the result is true for n equal to k. Suppose the result is true for n is equal to k, right? What is the meaning of that? So what is the meaning of that? That means d of x1 comma x2 comma and so on xk is equal to, so product I is equal to 1 to n, j is equal to 1 to n, I less than j, xj minus xi is true for any k values, any k numbers, x1, x2 and so on xk. It is independent of the whatever you choose. Okay, d of x1 x2 xk is this much. Okay, now we need to prove for n equal to k plus 1, right? So now consider n is equal to k plus 1. Okay, but I am taking this particular thing. Okay, now x1 comma x2 comma, so I will take that's okay, xk comma xk, but instead of xk I am taking x here, d of x1 x2 xk comma x. It's a variable now. Okay, are you okay? Fine. So this is a variable. These are fixed. Okay, so it is what? It is a determinant, right? So it is a determinant of what? 1 up to 1, x1 up to xk, and the last one is x. Okay, right. This is x1 square, x2 square, and so on, xk square, x square, right? So what is the last column? X1 power n minus 1. There is a small problem here. I have to go up to what?
K.
Yeah, so x1 power k only. So n variables, I am going up to n minus 1. Now k plus 1 variable. So I have to go x1 power k. Correct. X1 power k. And here x power k. Yeah. Okay. Now, if you find the determinant, what do you know? These are all fixed numbers, right? So what we can say about this this one, d of x1, x2, xn? Can you say something? What do you know about this? If you evaluate this, what is that it is? X is a variable, right? What is that you're going to get at the end? If I expand it, the determinant, yeah. What is
Polynomial
d?
in X.
Very good. So it is a polynomial in X of degree. So what is that we have? So these are all numbers. Only variables are here. 1x x square up to x power k. Single variable, of course. So powers of x are only in the last row. So a polynomial in x of degree, very easy.
Degree K.
Degree k, right? It is a polynomial of degree k. But we are working over fields. So it has at most k roots over fq. K roots over fq. So this part is also clear. Now, can you tell me some roots for this one? What is so I'm asking this question to you, right? So tell me this. What is d of x1 comma x2 comma and so on xk comma x1? What is this equal to? Okay, let us, I'm calling 0, right? Right now I'm calling is as equal to f of x. Okay, now I hope you agree. So polynomial in fx, it is equal to 0. Why? Because now last row becomes 1 x1. Yeah, so these two rows are same, right? So can you tell me now some roots for this polynomial? It implies
X1, X2 till
yeah,
Xk.
f of x has roots. This implies that x1, x2, xk are the roots of the polynomial, right? So very simple, easy. Yeah. So this implies x1 comma x2 comma and so on comma xk are. So I hope you are not feeling any difficulty. So it is not dependent on the previous your knowledge, right? Means in this course, it is a completely new. Those who joined today, I hope there is no difficulty. X1, x2, xk are roots of this fx, right? Then how fx look like? But we know that f of x has at most k roots only. Now these are all the roots, right? These are all the roots. Now how do you write? But where they belongs to? Further, these x1 comma x2 comma and so on xk, where they are from fq only. That is what my initial thing, and it is a polynomial in over fq only. So how polynomial f look like? Yeah, so this implies f of x equal to some a times, are you following, x minus x1 into x minus x2 into and so on x minus xk. Do you agree with me? Yeah, please respond.
So can you repeat?
What is that I'm saying? That see, these are the roots, right? X1 is a root, x2 is a root, xk is a root. What is f of x? F of x is this one. Okay, I'm calling this as f of x instead of writing every time d of x1, x2, xk comma x. This is a function. It's a polynomial in x of degree k, and it has at most n roots, and we know all the roots. So x minus x1 is a root, right? X1 is a root, so x minus x1 divides fx. X minus x2 divides fx. So f of x equal to a times x minus x1, x minus x2, x minus xk. Is it okay?
Yes, sir.
Yeah. But what is a? Okay. What is a here, right? A is the coefficient of, yeah, tell me something. What is A? A is the coefficient of, yes, coefficient of x power k, right? When you multiply, what happens? Right. These are all they are all dividing effects. So I wrote this, but into multiply by A also. Because x into x into x, x power k will come, and A will be the coefficient of x power k. Correct. Yeah. Now, can you tell me what is the quotient of x power k from this matrix? This is a determinant, correct?
Determinant of A K cross K.
Like that, right? AK, right?
AK.
Determinant of AK, okay? Oh, you are clear, yeah. So, but that is A is equal to determinant of AK, but that is I'm denoting it as D of x1, x2, and so on xk, correct? Yeah, yeah. So what is happening now? So my f of x equal to, right? So my f of x equal to, what is going to happen to f of x? My f of x equal to d of, so I'm writing again instead of f of x now, much more better way. Okay, so I'm writing it as, so d of x1 comma x2 and so on xk comma x is equal to d of x1 x2 and so on xk into x minus x1 and so on into x minus xk. Okay, this part is okay to you, correct? Now, but what is this d of x1 x2 xk by induction, right? By induction, you know answer for this. By induction, so this is equal to product I is equal to 1 to k, j is equal to 1 to k, right? J less than k, j less than I, yeah, xi minus xj minus xi, correct? Xj minus xi, okay, multiplied by this thing, x minus x1 into x minus xk. Now, can you tell me what is that I'm going to do next? Yeah. So
X
now
equal
I'm
to K plus 1 will write the result.
yeah, you substitute x equal to x. So x1, x2, and so on xk plus 1, right? Which is equal to, I'll get the this one. See here our x plus 1 minus xk, x plus k minus x2, and so on x plus xk plus 1 minus xk, that we are getting. So I is equal to 1 to k plus 1, j is equal to 1 to k plus 1, j less than I, correct? Multiplied by this xj minus xi. Yeah. Okay. Any questions? Yeah. So we are done. So please let me know any questions you have. Kanak, is it okay?
Yes, sir.
Yeah. Okay. So simple question to you. So what is the answer to this one? D equal determinant equal to 1 1 1, right? So 2 3 4, 2 square 3 square 4 square. Can you tell me what is the answer to this?
So 4 minus 3 into 4 minus 2.
4 minus 3 into 4 minus 2. Actually, we have 3 minus 2 also. Okay, that is 1. So we do not hold that. Yeah. So this is the answer, correct? Yeah. So that way, Now tell me that. Tell me this quantity now to me. Okay. What is that I am asking to you is that. Yeah, 1 minute. Yes. Okay. Tell me this quantity now. If my x1 comma x2 comma and so on xn are distinct, this implies what we can say about an. Yeah.
If all of them are distinct, then determinant of an will be non-zero.
Determinant of an is non-zero. So determinant of an is non-zero because this is simply x1 minus x, xn minus x1, x1 minus x2 and so on, right? And further, that means that an is non-singular matrix. Okay, and it has many other properties also. So can I proceed now? Till now everything fine? Nothing I done, right? Yeah. Kaustubh, can I proceed?
Yes, sir.
Yeah.
But okay.
Yeah, Mahek, are you clear with everything?
Yes, sir.
Okay. Now coming to actual now little bit of coding theory now. Okay. So very simple, but even then very simple. But you do not realize that I'm going to coding theory. Okay, we'll go very slowly. Okay. Yeah. So what is that I'm going to do now is that now let us start. Let FQ be a finite field. Let FQ be a finite field, right? And so x1 comma x2 comma. Okay. So if it is a finite field, what happening today? Sounds very sorry. Restore file. Yeah, I think this is going to be it. Okay, fine. I'm not sure what is going to happen to this file at the end. Okay. Yes. Okay. Yeah. Okay. Fine. So LFQ be a finite field and x1, x2, xn, right? X1, x2, xn be distinct elements. Okay. X1, x2, and up to xn belong to FQ be distinct elements. Okay, this is the first point. And second is that let us take B1 comma B2 comma and so on Bn belong to FQ, right? So now can you say something about
Sir, I can't see your screen.
Okay, right, thanks. Yeah, I understand. So that is crash. Yeah. Okay. Let FQ be a finite field, right? And x1, x2, xq be distinct elements. B1, B2 belong to FQ. So need not be distinct. Okay. These are need not be distinct. Are you able to see now?
Yes, sir.
Yeah. So these are need not be distinct. Okay, good. So it is like a Chinese remainder theorem like that only. So we have these are distinct, but means x1, x2, xn are relatively prime to mutually relatively prime. B1, B2, Bn are any numbers. Are in the linear transformations, you know that if I take a basis and I choose any n vectors, so there exists a unique linear transformation which takes them to them. Like that, all of them in the mathematics, all of them are very much equal. Yeah. Okay. Now, what is that I want to claim is that so now we can think of these are as a points, right? X1 comma B1. Okay. X1 comma B1. Now interpolation. X1 comma B1. x2 comma b2, right? And so on, xn comma bn. Okay. So what is that I want to claim is that there is a unique polynomial of degree at most n minus 1 such that how much degree? Yeah, n or n minus 1? N only. Degree at most n such that degree at most when directly n. There is unique polynomial of degree n such that, yeah, such that I'll write much properly. There exists a unique polynomial of okay, a0 plus a1x plus a2x square up to an x power n. Unique polynomial f of x equal to a0 plus a1x plus and so on plus an x power n of degree n. Okay, this belongs to fq of x. Yeah, with what property? Such that, can you say something? Yeah. So that for every I, f of xi is equal to bi. Are you following? Hello? Am I audible?
Yes, sir.
Yeah, okay. What is that I'm claiming? Fq is a finite field. So we have to I take n distinct elements, okay? B distinct elements, right? So now I took any need not be distinct, but n elements, right? Here distinct elements. Now I'm claiming that, so there is a unique polynomial, so such that f of xi equal to b, f xi goes to ba. Okay, yeah. So this is what I want to prove it. Yeah. So how to prove? Now proof. Okay. So what do you mean by f of x1 equal to b1? Somebody help me. F of x1 is equal to b1, f of x2 is equal to b2, and so on, right? F of xn is equal to bn. Yeah, can somebody help me? How do you write these things? Yes. Yeah, Kaustubh, go ahead. See, my f of x is this, right? What is, I'm not asking tough question. F of x is
A0 plus A1 x1 plus A2 x1
A0 plus A1
x1
x1 plus
A2
A2
x1
x1
plus up to right.
square,
Yes.
right? Yeah.
Yes, plus up till an x1 to the power n.
N. Okay, which is equal to
B1.
B1, right? It is equal to B1. Yeah, okay. Now I am taking another value, x2 I am substituting. That is A0 plus A1 x2 plus A2 x2 square. So I'm substituting x2 only, right? An x2 power n is equal to B2, right? So like that I have these I'm substituting. So finally, what is the last equation, right? So A0 plus A1 xn plus A2, right? Xn square and so on plus An xn power An xn power n is equal to Bn. Okay, let us convert them, and I am doing any mistake, let us verify that. Okay, so how do you convert it into matrix form, right? Yeah, so first row is 1, right? x1 square and so on, x1 power n. Okay, second row 1 x2 square and so on, x2 power n, right? So like that, what is the last row, right? 1 xn square and so on, xn power n plus 1 n, right? Yeah, so this is multiplied with what?
A0, A1,
A0 A1 up to an, okay, which is equal to b1 b2 up to bn. So there is some problem coming, right? There is some problem coming, right? So the problem is coming because I took the degree is I had to take degree n minus 1 only. Why? See, so a polynomial of degree 1 uniqueness के लिए, so degree of the polynomial should be n minus 1, correct? Linear polynomial can get unique linear polynomial when we have two roots, right? Right, 2 points. 2 points will give a unique line, correct? Yeah. So here it should be x power n minus 1, a n minus 1, x n minus 1. Okay, this is n minus 1. Okay, so degree.
Sir, can you repeat your last argument?
See, I take a linear polynomial f of x equal to ax plus b. So linear polynomial is uniquely determined by how many points? Now to get a line equation, how many points I want? Straight line, unique straight line ke liye how many points are required?
2.
2 points, right? 2 points will give me a linear equation. So degree 1 less, right? Yeah.
Yes, sir. Yes.
Yeah. So I had to take, so n plus 1 points means I'll get a unique polynomial of degree n minus 1. Okay. Yeah. So here all these things are now changed to n minus 1. Okay. Na? So this is n minus 1, a n minus 1, a n minus 1, right? Here n minus 1, right? So, but these are x1, x2, xn, they are same. There is no problem with them. Yeah. Any questions? I think actually I just wantedly wrote like that. Now I am modified here so that you will all be clear about that. In order to get a degree 2 polynomial quadratic, then I need at least 3 points. Parabola need size, need 3 points. Sorry, circle or parabola. So they need 3 points to determine uniquely, right? Like that. Geometrically also you can think of. Yeah. Okay. So now this is a here n minus 1, n minus 1, n minus 1, here a n minus 1. Now everything is matched. Now what is the size of the matrix now? Here also n cross n. So this is n cross 1, this is n cross 1. Everything matched. Are you okay?
Yes, sir.
Only thing is that here I made n minus 1, but it's this a n minus 1. Okay. So I'll write much more clearly here one more time, so that it will be, so that will be clear to you. Correct. Yeah. So let me write that. Yeah. Please think, start thinking what is the next steps and all, right? Of degree n minus 1. Okay. There is a unique polynomial fx of degree n minus 1 such that f of x equal to ba. Yeah. So I converted them into like this, right? Yeah. So let me write this also little clearly. Yeah. Yeah. So you can ask me any questions you have in the meantime. Yeah. A n minus 1, x2 power n minus 1 plus a n minus 1 xn power n minus 1. Yeah. Now tell me that what is happening. Now it is of the form ax. This is, you know, it is an exactly, right? An into some vector a is equal to vector b, right? A is this a0 a1 an minus 1, correct? Yeah. Any questions? Why this polynomial is unique now? Can you tell me?
So this
No?
an is non-singular, so
Right.
we have a unique solution.
Yeah. Now an determinant of an is not equal to 0. So a is equal to an inverse into b, right? So unique solution. Yeah, very simple and easy, right? How matrix theory is coming into picture, right? Beautiful, right? So this is how all the interpolation techniques will work. This is called Vandermode matrix. See, this comes very naturally in Vandermode matrix, substituting the values in the polynomial. So this matrix, whatever you think of earlier, it is came very nicely as a matrix, right? That Vandermode matrix. Now, if all these roots are distinct, then this is determinant is not equal to 0. I have a unique solution. So the conclusion is that if you have n distinct points, and so then there is a unique polynomial which takes x1 to b1, x2 to b2, and xn to bn. But the degree of that polynomial is n minus. Yeah. Any questions?
Hello, sir.
Yeah, please. Yeah.
Where are we using the fact that it is from finite field?
So actually it is not required. Finite field, anyway, a field is sufficient. Finite field is not required. Yeah. So here finite field is not required. Field is sufficient. Since in our course we are working in finite field, so I am taking my field as finite field, but you do not require. Only thing now finite field comes into picture now. What we can say about n value? Can you say now? These are distinct elements, now. So can you say something? Yes.
What n? What was that? What question?
Yeah. See, FQ is a finite field.
Hmm.
How many elements will be there in FQ?
Q many.
Q elements.
Hmm.
Now x1, x2, xn be distinct elements, right?
Yes.
In FQ. Yeah. So what we can say about n and q then?
N is less than Q.
Less than or equal to q.
Less than or equal to.
That is, you know, right? This much is clear? Yes.
Yes, sir.
Yeah. This is what the beauty is. Okay. So that is only I can say n is less than or equal to q here. In the finite field, I cannot take how many distinct I can get, at most n only. Yeah.
Yeah.
Not more than that. Otherwise, there is no difference actually, finite field or field. You are absolutely correct. Very, very pertinent question you asked. So this entire thing business will work for any field, real numbers, complex, wherever. Yeah. Now, actually, now we are going towards our business. Okay. Before that, so I want to tell few things again, right? So I open new page for that. Let FQ be a finite field again, right? Let FQ be a finite field. See, why I'm writing again and again, because I want to tell you that we are going one layer after another. First, only we consider the AN, determinant and all, okay? So if x1 next to xn are distinct, we showed that determinant P not equal to 0. It is non-singular matrix. Then we showed one result. Okay, so here you take n distinct point, then there is a polynomial of degree n minus 1, unique polynomial, which takes x1 to b1, x2 to b2, x1, xn to bn. Okay, yes. Now let FQ be a finite field, and we denote PK. Okay, PK be, let PK be set of all polynomials be the set of all polynomials of degree less than or equal to k. Okay, with coefficients from fq. Okay, yeah. Okay, so what is it actually? pk is pk equal to all f belong to fq of x. Okay, such that so f of x is equal to a naught plus a1 x plus and so on plus ak x power k. Yeah, otherwise, okay, better I write this way. Okay, so let me erase this. You start thinking. Okay, so first I write polynomial and then I'll tell the coefficients are from fq, right? Yeah, so what is f? Yeah, what is pk? So pk is equal to a naught plus a1 x plus and so on plus ak x power k, so that ai belong to fq. Okay, how I'll get a polynomial degree less than k from here? I am allowed to take these a's are 0 also, right? If my ak is 0, then I'll get a polynomial strictly less than k. Okay, na? Are you okay? It is capturing
Yes, sir.
all the polynomials of degree at most k, right? So what do you know about pk? What do you know about pk and fq of x? Yeah, you know something? Set of all polynomials of degree less than or equal to k. You know something about it?
Subset of.
Not only subset, it is a vector subspace.
Oh.
Yeah, subspace of fq of x of dimension
Dimension k.
k. Let us what we do. We take k minus 1. Okay, then its dimension becomes, yeah, then its dimension becomes k, right? Yeah, okay. pk, but pk I wrote here. Okay, so k plus 1. Okay, let us write k minus 1 only because yeah. Wait a minute, Tijan. Polynomial of degree, yeah, it's okay. Yeah, but you also be careful when I'm writing something, right? What is that I do later? I'll substitute x1 is 2 k. Yeah, I'll take k minus 1. Huh? Let us see later if a possible comes. We'll see that. Otherwise, pk minus 1. Yeah, no problem. So pk minus 1. Yeah, so okay, here I'll write pk is the polynomials of degree k with quotient from fq. So I wrote pk minus 1 here. That's okay. So pk minus 1 is equal to this, where a belongs to. So then a vector space of fq of x of dimension k. Are you understanding this dimension ky? Yeah, connect. Do you know the reason why dimension is k? What is the basis?
All the coefficients of
No,
x,
no,
right?
no. So you know R of x, real numbers. R of x is set of all polynomials with coefficients from real numbers, right?
Yes, sir.
Yeah. What is it a vector space over R?
Yes, sir, it is.
It is vector space over R. Okay. What is its dimension? Okay. If I take any element here, how it look like? So for example, if I take an element here, so for example, is 1 plus 3x plus 5x square, is it belong to here?
Yes, sir.
Yes, right. So if I give some other polynomial, then how they give, right? They say that a naught plus some a1x plus a2x square, something, right? Yeah. So polynomial changes, what are changing? What are fixed? So what is the basis? Okay. So complex numbers is a vector space over R, right? So what is the basis? So with that, try to think and tell me now. Yeah.
Sir, a naught. Sorry, 1 x square, so on.
1x square up to x power k minus 1. Because polynomial changes, coefficient changes. So, but these 1x square up to x power k minus 1, they will change. They will not change, right? So the basis is 1x square up to x power k minus 1, right? Yeah. Any questions? Are you following? Everything is a linear combination of these, right? So pk minus 1 is a span of this, right? Yeah. Okay. So any polynomial I take, that is a linear combination of these things. So every polynomial of degree k minus 1 is actually linear combination of these. So it is a basis. And you can easily prove that a naught into a1x plus I take equal to 0 polynomial, then all coefficients has to be 0. So it is linearly independent and their combination is this. So it is a vector space, subspace of dimension k. Yeah. So I hope everything is okay till now. Any questions till now? Okay, good. Now I'm going to that business again. Okay. So I'm now introduced to three things till now. First one is Vandermode matrix and whose determinant. Next one is that there is a unique polynomial with if I take n distinct points, k distinct points, and any k numbers, then there is unique polynomial taking xi to bi. Okay. Now I just defined, you know this, but I recalled you that polynomials of degree k minus 1, how it look like, and its dimension k, and whose basis is this. Yeah, till now fine. Now I'm going to that RS codes now, coding theory, linear codes. Yeah. So now coming to that business. So any questions till now? Please let me know. So it is now independent, till now independent, but even now also most of it independent. You do not feel that we are doing something coding theory. So let FQ be a finite field. Okay. So now you know that FQ minus 0, right, is a cyclic group. Is a cyclic group, correct? So then it is generated by single element. Generated by single element, correct? Yeah. Okay. So how it is denoted? So FQ minus 0, right? This FQ minus 0 is equal to some elements, right? So can somebody help me? So let us say generated by single element, say alpha. Now can you tell me what is FQ minus 0 look like, elements look like? FQ is a finite field. You know that it is a group with respect to addition, and if you remove 0, it is a group with respect to multiplication. Further, we know that it is a cyclic group with respect to multiplication. So it has a generator, say alpha. How many elements are there in FQ minus 0?
Q minus 1.
Q minus 1. and alpha is a generator, right? The order of this group is q minus 1, right? Yeah, so can you tell me the elements in this?
Alpha square.
First one, right?
1. Yeah.
Alpha square. What is the last thing? Last one.
Alpha q minus 2.
Very good. Wonderful. Wonderful. Alpha power q minus 2. Yeah, good. Because alpha power q minus 1 becomes 1. Right? Yeah. So it is simply alpha power q minus 2. But number of elements are total number of elements are q minus 1 because I'm starting from alpha power 0, right? So you can call it as alpha power 0. Yeah. Okay, good. Nice. So now my n equal to, I told you, here n value is less than, right? So I took x1 x2 xn. So as you rightly pointed out, what is that finite field is coming here? No finite field business actually. So this x1 x2 xn, n is less than or equal to q, right? So I'm taking my n is equal to now, yeah, so by excluding 0 also I'm taking only non-zero elements. Now my n is equal to q minus 1, right? Now how do you write this now? This set n equal to q minus 1, so it is 1 alpha square up to, can somebody help me? Alpha power
So
no,
can you scroll up? What is n?
n is here, I took n is here only. The thing, this is given n equal to q minus 1. I'm asking that how do you write this, right? Nothing. It is n minus 1, right? It is q minus 2, n equal to q minus 1, so n minus 1. Nothing, n is nothing. Here only came. Are you okay?
Sir. Yes, sir.
Each one is independent topic, okay? Don't worry about the previous one. So each one is independent, but why I'm connecting it here, fq be a finite field, x1 and xn be the distinct elements in fq. When they are distinct, but fq contains q elements, so n is less than or equal to q. That is just earlier I am just connecting it. Yeah. Now I took now maximum, almost maximum possible value, n equal to q minus 1 I took. Of course, q also I can take, but non-zero values I'm taking. All the non-zero. But what is these non-zero values? They are actually the, it forms a group. Now these elements also, very interesting element. This forms a cyclic group and alpha is a generator. Yeah. Okay. Very nice. Okay, so till now fine, everything fine. Now I'm taking the that the k is my k is less than n. Okay, actually less than or equal to n, but actually k is very, very small. It's very small in comparison to, do you know why this k and n now coding theory comes? Do you remember that what is this k and n? Yeah, so what is this n generally in coding theory?
Length of the code?
Length of the code, very good. Or length of the code words, or you will call length of the code also, correct? Code words are of length n. What is the k? You forgot what is k?
Dimension.
Dimension of the code. Dimension of the code, right? So that is C is a k-dimensional vector space. Yeah. So now I want to construct now code, okay, by using whatever we done. Okay, very simple. Don't worry about anything. Okay, what is that I do is that I'm mapping now. So code, what is code actually? Code is a map, right? Map from fq power k to, right, fq power n, correct? So somehow I need to map like this, correct? Yeah. Okay. So, okay, I'm defining now C. My C I'm defining. So code I'm defining. Okay. My code is equal to, so for that one, yeah. So my code is equal to f of 1, f of alpha, right? F of alpha power n minus 1, right? What is this f here? F belong to pk minus 1. Are you following? Yeah. Are you okay? Okay. So actually this fq power k I told, but actually this is now it is a vector space over fq of degree dimension k. That is my pk minus 1 actually, right? So pk minus 1 to fq power n. Okay, it is isomorphic to what? Fq power k only. Why? You take a polynomial, right? So a naught plus a1x plus and so on plus a k minus 1 x power k minus 1. This belong to pk minus 1, right? If this belong to pk minus 1, okay. So what is the corresponding element in fq power k? This is a k minus 1, right? This belong to fq power k. So there is no difference between these two, right? Both are vector spaces. Okay. So I can
Hello,
think
sir.
of, yes, please.
There is a box where you are writing.
Yeah. Okay. Now,
Ah,
yeah. Yeah. So, so what is it I'm saying is that polynomial and this vector both are same. So polynomial is same as that coefficients only, right? So this is a polynomial. So these two are isomorphic. So so I am converting the a naught a1 ak minus 1 to, now I am substituting. It is called evaluation map. Okay. So this is evaluation map. Okay. So I am writing it as evaluation. So evaluation pk minus 1 to fq power n. Okay. How it is going? So it is taking my polynomial fx mapped to where? So it is mapped to f of 1, f of alpha, and so on, f of alpha power n minus 1. Okay. So now, so when I substitute 1, f is a polynomial from fq. So it is sum of the coefficients, right? So like that, just I'm evaluating it. Yeah. So we can easily check that it is a linear map. Why it is a linear map? Yeah. So I'm just leaving it to you to check it is a linear map. These are two vector spaces. It is a linear map. What is 0 element goes to? 0 polynomial. My polynomial is 0 polynomial. Where it goes to? Hello?
all 0, 0, 0.
So 0, 0, 0. So 0 vector goes to 0 vector, and like that you can easily check that there is no problem, but it's a linear map. So since it is a linear map takes vector spaces to vector spaces. Otherwise, you can directly check here. Okay, I'll check directly instead of these things, right? Yeah. So yeah, so check that one time that so let us call this evaluation map. Evaluation of f is equal to what? F of 1 comma f of alpha and so on, f of alpha power n minus 1, right? What is evaluation of g, right? G of 1, g of alpha and so on, g of alpha power n minus 1, right? Yeah. Now what is evaluation of f plus g, right? Right. It is equal to f of 1 plus g of 1 and so on plus f of alpha n minus 1 plus g of alpha n minus 1. I hope you can easily check that it is evaluation of f plus evaluation of g. Is it okay, Achila? Can I?
Yes, sir.
Yeah. So similarly, evaluation of alpha f equal to alpha times alpha f is a map, is a function, is a polynomial. So polynomial multiplied, alpha multiplied each and every term. So alpha a naught plus alpha a1 like that. I hope you understand, right? So alpha, it is equal to alpha times evaluation of f hoga, right? So easy to check. So it is a linear map. And what is the kernel of this map? That is interesting. So for example, evaluation of h is equal to 0. What is the meaning of that? Yeah, can you tell me? What is evaluation of h actually? Yeah, please participate. Okay, this is h of 1, h of alpha. I'll prove other way also. H of alpha square, and so on, h of alpha power n minus 1, which is equal to 0 comma 0, correct? Kernel, which is in the kernel. Okay, let h belong to kernel of evaluation map. Okay, so then this is equal to 0 0 0. So that means what is that means? H of 1 is equal to 0, h of alpha is equal to 0, and so on, h of alpha power n minus 1 is equal to 0. But what do you know about h? Yes, please. Yes. Yeah, what do you know about h? Yeah, please. What is h actually? What is f, g and all? Why you are not speaking?
Polynomials in pk.
Polynomials of degree?
K minus 1.
K minus 1, correct. So, but dimension is k, because constant term is also there, right? Dimension is k, but there are polynomials of degree k minus 1. H is a polynomial of degree k minus 1, right? So in fact, here I can take less than or equal to also, because so here I can take less than or equal to also. Where here there is not a problem, because I'm taking polynomial of degree less than degree k minus 1. So k minus 1 is less than, strictly less than n. So it is not a problem, right? Yeah. Okay, good. So, but h is a polynomial of degree k minus 1. Then what we can say about h? How many roots we have here? You see here, how many roots are there for h? Please tell me. H of 1 equal to 0, h of alpha equal to 0, h of alpha power n minus 1 equal to 0.
N roots.
N roots are there, but n is bigger than k minus 1, correct? Okay. Yeah. But h is a polynomial of degree k minus 1, implies h has at most k minus 1 roots only. So we proved that earlier. You take any polynomial over finite over field of degree k has at most k roots. We proved that. Now h is a polynomial of degree k minus 1. It has at most k minus 1 roots, but k minus 1 is less than n. Okay. So this implies that what we can say about h, which polynomial satisfy more roots than the degree?
0 polynomial.
0 polynomial, right? Identically 0. So that is what the claim is. So if you do not happy with this approach, okay, so I will tell you in a different way. What is the different way? So so look at here. So Okay, so look at here. So let us say h is equal to h naught plus. So I am bringing that what we done today, so that will also help you. Okay, now h of 1 is equal to 0, right? H of alpha is equal to 0, right? And so on like that. H of alpha power n minus 1 is equal to 0. Correct? We have this, right? Good, nice. Now, how do you convert it into matrix theory? You know, right? So this is h naught. Sorry. Do you remember that? H of 1 equal to 0. What is the meaning? Okay, I'll write one time so that it will be clear to you. Okay, this is h of x. H of x is equal to this, right? What is h of 1? Right? H naught plus h1 hk minus 1 is equal to 0. What is h of alpha? H of alpha is h naught plus h1 alpha plus and so on plus k minus 1 alpha power k is equal to 0. K minus 1. So h of alpha square. What is this value equal to? H naught plus h1 alpha square and so on plus hk minus 1. Can you tell me? Alpha square power k minus 1 is equal to 0. Yeah, I hope you are clear with what is the last one. Yeah, please. H of alpha power n minus 1, which is equal to h naught plus h1 power alpha power n minus 1 and hk minus 1. Yeah, can you tell me here what is it I have to write?
Alpha raised to
Alpha raised power. Be careful, go slowly, tell me systematically. So alpha, h of alpha, h of x is this, nothing is there. I'm just substituting alpha here. Okay, when I substitute alpha, I'll get alpha power k minus 1 is the last term. When I substitute alpha square, every place x जगह पे alpha square substitute कर रहा हूँ, right? यहाँ होगा alpha square power k minus 1. अभी मैंने alpha power n minus 1 substitute कर रहा हूँ. Yeah, h1 alpha power n minus 1. What is the last one? Yeah.
alpha power n minus 1 power k minus 1.
Yeah. So into k minus 1, okay, is equal to 0, right? Yeah. Convert into matrix now. Right? Is equal to 0. Correct. So what is the first column? Yeah, or first row, whatever you can call. Okay. First row now becomes 1 alpha square up to what is the last one? Alpha power n minus 1. Right. What is second row? 1 alpha power alpha square. I'm substituting alpha first, right? So there is a small problem, right? You have to point out what is the mistake I'm done here. Tell me quickly. First row also mistake, but there are other mistake also. You need to tell me fast. Yes. What is my first row? 1 only, right? What happened, please? What is my first row? How do you convert into matrix?
1 1 1
1 1 1 1. How many ones? So how many ones? How many
k
ones?
ones.
K ones. Okay, right. So what is next row? 1 alpha, right? Alpha square. Yeah. What is the last one here? I'm substituting alpha here. Alpha in this polynomial. Yeah. What is the last one?
Alpha to the power k minus 1.
Alpha power k minus 1. Second, third row, right? One more row I'll write. Alpha square I'm substituting. 2 into 2, right? So like that alpha square into k minus 1. Right? Yeah. So like that. So nth row. Yeah, alpha power n minus 1. Why nth row I told is the first row, second row. Alpha power 0 is the first row. Alpha power n minus 1 into 2. Right? Alpha power n minus 1 into k minus 1. Yeah, this determinant, this matrix, right? Multiplied with what? H0, H1 up to
HK minus 1.
HK minus 1. So this is equal to 0, 0 up to 0, right? Yeah. Now tell me what is the size of the matrix, correct? What is the size of the matrix, right? This is how many rows are there? Right?
N cross K.
N cross K, right? And you know that so these are actually, what do you know about 1 alpha alpha square up to alpha power k minus n alpha power n minus 1? I'm writing here. What do you know? What do you know about 1 alpha alpha square up to alpha power n minus 1? We know about them. These are what exactly?
Distinct.
They are distinct, yeah. What do you know about? They are distinct. In fact, they are actually all the elements in the finite field fq minus 0. They're all distinct. I hope you are enjoying. Actually, very nice topic. Actually, okay, yeah. So they're all distinct. So if they are distinct, you know that I can construct even up to, I go to up to Vandermode matrix. I can construct, right? You remember that Vandermode matrix? I can even go to. I can include more columns. So this is a, in that Vandermode matrix, these are the first k columns. Are you following that? So these are first k columns. Do you remember that what is the first row, first column in Vandermonde? 1 1 1 1 1. What is the second column? X1, X2, X3, Xn, right? Now what are my X1, X2, Xn? X1, X2, X3, Xn. My X1 is 1, X2 is alpha. Are you following? X1, X2, X3, Xn. X1 square, X2 square, X3 square. Okay. Is it, are you following? Is it beautiful?
Yes, sir. Yes.
Yeah, right. So that much only. These are the first k columns of Vandermonde matrix. So what do you know about first k columns of Vandermonde matrix? They are linearly independent, right? So because of that, so the null space contains, null space is 0. Okay. So I proved it, but I proved in a different way also, both the ways. So these are all same actually. So yeah. So I just gave one more time. Yeah. Okay, fine. So finally, come to the conclusion that my C, coming to the C again, code. Okay, these are the codes. What are the codes? My this C is equal to f of 1, f of alpha, right? F of alpha for n minus 1. But what are these f's? F belong to pk minus 1, right? So this is polynomial of degree k minus 1, right? So I'm changing the polynomials. So let us think of 1 alpha power n minus 1 are fixed. F are varying. Oh, okay. F are varying. They are varying. So what is the dimension of, what is the cardinality of C now? Yeah. Cardinality of pk minus 1, correct. So to show that one, I want to show that already we know that it is both are vector spaces. So I want to show that if I take two distinct polynomials, so they will give the, they are distinct, okay, with distinct vectors here. Okay, let f comma g belong to pk minus 1. Okay, f comma g belong to pk minus 1, right? So suppose f not equal to g, right? So claim is that f of 1, f of alpha, and so on, f of alpha power n minus 1 is not equal to this vector. Okay, is not equal to g of 1 up to g of alpha power n minus 1. These are also not equal. Okay, we'll prove by contradiction. Suppose they are equal. Suppose equal. That implies what? F minus g of 1, right? Right. F minus g of alpha power n minus 1 is equal to 0. 0 polynomial, right? 0, yeah. So 0 vector. That means what happening? Can you say somebody now? Can you comment? But f minus g is a polynomial of degree. Yes. Less than or equal to k minus 1. So it has n roots. N is greater than k minus 1. So what we can say now? F minus g is identically equal to 0. Right? So that is a contradiction, right? So f minus g equal to 0, but we have took that f is not equal to g, right? So we got the required contradiction. Yeah, any questions? Okay, so I'll just I'll give some gap to you. So because we are doing continuously, so then we'll meet again at 10 o'clock. 5 minutes we take gap and again we start, right? Yeah, okay. Okay, so what we done till now is that this C is a code now. Okay, so C is equal to, write one more time. So this is f of 1, f of alpha, right? F of alpha power n minus 1, right? This thing. So vector. So this belong to f cube power n, where now f belong to pk minus 1. F belong to pk minus 1. Okay, so it is a linear code. Right? So we already proved that actually this is image of evaluation map, right? Evaluation map EV. Okay, it is a map from pk minus 1 to so f cube power n. Okay, and we also proved that so it is its cardinality is isomorphic to exactly pk minus 1, right? So and further we show so dimension of C is equal to k. That means C is n comma k code. Yeah, so we'll understand more what is generating matrix and all, right? So we'll try to understand them now. Okay, so can you predict that what is actually generating matrix contains? Okay, so tell me first of all, what is the size of G? Yeah, you know, right? What is the size of the generating matrix? Yes, please. Don't worry about now n comma k code. What is the size of the generating matrix?
K cross n.
K cross n, correct. So I need to know k rows and n columns, right? So n columns are coming this putting 1 to up to alpha power n minus 1, correct? So what are these 1 alpha power n minus? These are exactly the elements of fq minus 0, right? Base field fq minus 0. So these are the finite field with that is a cyclic group generated by alpha, right? So now what we can expect? Which polynomials I have to consider? Yeah, so that I'm going to tell you now. Okay, so what is the basis for pk minus 1? Two questions now. The second question is this: what is the basis for pk minus 1? You understand that, right? Tell me. One x
1x square
up to x power k minus 1, right? This is the basis for pk minus 1, polynomials of degree k minus 1. So I can substitute here first. Okay, so my g is equal to, so first to substitute for 1 in the polynomial of 1, I am substituting 1 alpha up to alpha power n minus 1, right? So so I am writing here, this is evaluation of evaluation map of evaluation of 1. Okay, evaluation of 1. So let us write neatly. So it is so we are taking a map, right? Evaluation map. So evaluation of 1, evaluation of x, and so on, evaluation of x power k minus 1, right? What is this actually? Okay, so let us try to understand. So one in the one, if I'm putting 1 alpha square, what I am going to get? 1 only, right? So 1 of alpha square up to 1 of alpha power n minus 1. Now in the place of x, now my polynomial is x. Now my f is x. Now f of 1, f of 2, x of 1, right? So it is 1. Can you somebody tell me? Evaluating polynomial is x. This is my thing, right? F of 1, f of alpha, f of alpha power n minus 1. Now my f of x equal to x. F of x equal to first 1, f of x equal to x, f of x equal to x square. These are my rows. Now can you somebody help me to tell what is the second row? Evaluation of x, f of x equal to x. Yeah, please.
Alpha square.
So alpha square up to alpha power
n minus 1.
n minus 1. Yeah. So next, what is that function? What is the next function? Okay, let me write much more better way, right? Yeah. So this is so evaluation of x square, right? So like that. So evaluation of x power k minus 1. Yeah, k minus 1 polynomials I'm taking. Yeah. What is the next one? One more row will help here. Generally,
Alpha square. Alpha square, yeah, alpha root 4.
Yeah, right. Alpha
minus 1 square.
n minus 1, correct. So here 1 alpha power k minus 1.
K minus 1.
Yeah. Alpha
square
whole square. Yeah. So alpha k minus 1
n minus
1, right? Yeah. Good. Nice. Okay. So so let us write neatly. Okay. So my g is equal to, let us say, gij. Okay. So my g is equal to gij. Okay. So can you say me what is gij value? Yeah. So take time and tell me clearly what is this equal to. So it is powers of alpha, right? You see that these are all powers of alpha. So now I'm asking, can you say what is a ijth term here? Is it equal to alpha power I minus 1 into j minus 1? Are you okay? So 1 less than or equal to I less than or equal to k, right? 1 less than or equal to j less than or equal to, can you say something?
N.
No, be careful. N, n only, correct. Yeah, because n columns, right? So, but what is problem here? First row पे थोड़ा problem हो रही है ना? So I need to better start from what? See, so first column you look at here. In the first column, row is changing. So here also I need to get 0. So I think I have to, j value starts from 0, correct? No, but if j starts from 0, yeah, no, that n minus 1 is taking care. Yeah, correct. Right. So it is 1. So 1 minus 1, 0. So yeah, it is n, correct. Okay, good, nice. Any questions? Okay. So Gij is like this, and so I is from 1 to k. Yeah. J is from 1 to n. Yeah. So it is like this. Gij is so. Is it every one of you clear with the matrix G?
Yes.
Yeah. Okay. So yeah. So think about again one more time. Carefully go through. Okay, now little magic now comes. Okay, I need a this matrix, right? So I am constructing some matrix. Okay, because time is running up, so I'm just defining one thing and then we'll check things. Okay, how it comes we'll see if time permits later, right? So I am constructing giving a matrix to you. So what is that I'm doing now? So here I'm taking 1 alpha square up to alpha power n minus 1. Yeah. So 1 alpha square alpha 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 square whole square alpha power n minus 1 square alpha square power n minus 1, right? Yeah. Okay. So what is the last row I am taking? That so here I am taking 1 alpha power n minus k. Yeah. Alpha power n minus k square. So alpha square whole power. So basically nothing actually. You know that so C perp ka dimension is n minus k, right? So I am constructing that way. Yeah. So can somebody help me? What is the size of this matrix? Yes.
N minus k cross by n.
N minus k cross n. Okay. And one more thing is that you can check that how element here look like. If my h is equal to hij, right? So then how hij look like? Yeah. So can you figure out that? Hij value equal to, so it is equal to what? Yeah. alpha power
I minus 1 and j
no I
minus
minus
1.
1 I. So that is important.
Alpha power I and
j minus 1. Yeah. See, so j value when the first column entire thing is 0. So j minus 1 is required. But when row is not 0, right? All row is changing. All I value changing, right? So alpha power I into j minus 1, right? So no need to write this bracket. So and now you look at carefully, check. Okay. So into j minus 1, right? And here 1 is less than or equal to I is less than or equal to what? Okay. 1 is less than or equal to j is less than or equal to what? That we need to tell. Yeah. So it is okay n, and it is also clear, right? It is n minus k. Right. Okay. This part is okay. Now we are going to the final stage. Okay. So now I want to show that this is a parity check matrix. Okay. So you look at carefully. Yeah. Okay. We'll come back to that. Anyway. Yeah. Here only till now everything is going well, logic and all. So suddenly this matrix H came, but this is also not very complicated thing. So n minus k cross n, but why you choose entries like this? That is the only thing you need to be understood. That we'll try to prove it. Yeah, but before that, so look at this H, G into H transpose. Okay, call this as some matrix C. Okay, not C. So C already I took G, H. So let us take L. Okay, L. Okay, now my objective is that L is equal to Lij. Okay, so what is that you are expecting? What is H into G into H transpose has to be? To show H is a parity check matrix, what is that I want to show? Those who are attending coding theory classes, they can tell now.
0, 0.
0.
0 vector.
It is a 0 matrix. Okay. What is the size of this matrix, right? So let us see. So G is a K cross N, correct? And this is N cross H transpose, right? Coming to H transpose, N cross N minus K. So this is K cross N minus K matrix. Are you okay? Are you clear? Yeah, okay. This is my K cross N and this is my N cross N minus K. So H is N minus K cross N. Okay, H transpose I am taking. So I want to show that Lij equal to 0. So climb is, so Lij is equal to 0 for every I comma j, right? So basically, can you somebody tell me what is actually Lij? So I have G, right? I have G and I have H transpose, right? Here, right? Here I'm multiplying row and here I'm multiplying to column, right? So this into this plus this into this plus like that, right? So G is K cross N, correct? And this is N cross N minus K. Okay. What is the column here? First column. What is the first column? H transpose. Okay, fine. You're not following. How do you multiply two matrices? This row is multiplied to column, right? That is exactly what? This into this plus this into this plus like that you multiply and add, right? What is that actually in the vectors? If I take two vectors, multiply and add, what is that?
Taking dot product.
Taking dot product. Okay. So can you tell me now Lij is what? Lij is dot product of
Ith row and jth column.
Column or jth column of H transpose. Yeah, correct. Ith row of G and jth column of H transpose. Yeah. So can you say much more now? This implies it is a dot product of, yeah.
I throw J and one second.
Dot product of dot product of, oh, so I already wrote here. Yeah, tell me. Dot product of ith row of G with
Jth row of H.
jth row of H. Jth row of H. Okay, but so what is that again? Okay, so it is equal to, so Lij value is equal to now. So you know that so k is equal to 1 to how long I go, right? So k is equal to 1 to n. Let us see whether I am correct or not. Okay, so how many rows are there, right? So in a row pay, how many elements are there in Gth row? Number of columns in G is n, right? So I am taking G, I, K. I is fixed, J is fixed. Okay, here K is changing. So what is GI? So okay, let me write, and again this we write later. Yeah, so that it will be much more clear to you. Yeah. So otherwise, matrix multiplication only I am doing. How do you write matrix multiplication? I'm explaining one more time. So this is what is that ith row of J, ith row of G, right? Ith row of G is G I1, okay, and jth row of J. So H J1, right, plus G I2, right, J H J2, right. So please be careful that why I'm getting again here. You know that in matrix multiplication, K here K will come, but I'm multiplying with H transpose, okay, but I'm writing in terms of H. That's why it is like that. Don't you will understand that is not much problem.
Yes, sir. Yes.
So H J N here. Okay. Now let us write this now. It is equal to, so summation. So K is equal to 1 to N. So G I K H J K. Yeah, K is only changing. Okay. So jth row multiplied with ith row of G multiplied with jth row of H. Okay. But what are the values? We already know, right? Let them write. Yeah, with that we are going to complete. Yeah. Okay. So thing is that this is equal to, so summation. So K is equal to 1 to N. What is GIK? You remember, right? Alpha power I minus 1 into K minus 1, correct. HJK, how it is? Alpha power J into K minus 1. You remember that? In HPay, so it is like this, right? A row, there is no problem. Column, J minus 1, right? Yeah, okay. So this is equal to what now? Okay, so this we need to write. Okay, so Lij is equal to, yeah, summation. So K is equal to 1 to N. Yeah. So I can take alpha power. So this K minus 1 into how much? Here also K minus 1 is there. I'm adding them first, then I'm subtracting.
I plus J minus 1.
I plus J minus 1. Right. Okay. So that is nothing but here I and J are fixed. So it is the summation is depends upon K minus 1. So what is that I will do? I will write this as summation K is equal to 1 to N alpha power I plus J minus 1 entire power K minus 1. Right. Yeah. So I hope no problems. So if you expand it, K is changing, right? K equal to 1 to N, right? So this is alpha. So I'm taking this entire quantity as beta. Okay, this entire quantity as beta. Okay, So you will easily see that. So k equal to 1, 2, right? So beta power. So 1 plus beta power. What is the last value?
n minus 1.
Yeah. But this is equal to what? Beta power n minus 1 by beta minus 1. You remember that?
Yes, sir.
Yeah. Okay. Yeah. So now coming to this business. Okay. Beta minus 1. Okay. Now look at here. My beta is equal to alpha power I plus j minus 1. Right. But I is ranging from where to where. Right. So I is ranging from 1 to. So let me see one. So I value, I is from here, right? So I is changing from 1 to, you remember that? Yeah, here. I is ranging from 1 to k, right? J is ranging from, J is coming from here, not there, in H. In H. J is coming from H. But again, it is a row. So n minus k. Okay, let me write that properly here. Yeah. So one minute. Think about you also. What is that we need to write? 1 minute. Yeah. So my one is less than or equal to I is less than or equal to k. This I have, right? And also have 1 is less than or equal to j is less than or equal to n minus k. Okay. Jth row of H, right? How many rows are there in H? There are n minus k rows are there in H. How many rows are there in G? K rows are there. So this is the thing. Okay. Now what about this value I plus j minus k? Correct. So this is what is the maximum value? This is less than or equal to maximum value of I is k, na? K plus n minus k, right? Minus 1. Correct. So this is equal to n minus 1, but this is strictly less than n. Okay. So conclusion is that, what is the conclusion here? So I'm writing here, I plus j minus 1 is less than, so small problem. One small problem is coming for me. I made a mistake there. 1 minute. Yeah, it is less than or equal to n minus 1 is fine. Okay. I understand. So what is so I confused with that q minus 1 and n minus 1. N minus 1 is q minus 2. So there I confused actually. Sorry for that. Yeah. Right. So then what we can say about this alpha power I plus j minus 1? You know, alpha is a primitive root, right? How much power alpha becomes 1? You remember that? Are you following? You remember that alpha is a primitive root, right? Alpha is a generator. You remember that? This is last.
Yes,
Yeah, alpha is the generator for FQ, right? FQ minus 0. So alpha power Q minus 1 only 1. So alpha power Q minus 2 is not equal to 1, right? So alpha power I is not 1 before that, right? Yeah. So order of alpha is Q minus 1, right? So whenever my power something is less than that, it is not 1, right? Order of alpha equal to Q minus 1, right? So this we know, right? So sorry, I just confused here because n minus 1 is n is Q minus 1, so no problem. So this is not equal to 1. So this is non-zero. But what about alpha power n, beta power n? Yeah. What is beta power n? Okay. Do you want me to write below? Yeah. So one more time, write. Is equal to beta power. Beta is alpha ij, right? Alpha power. So alpha power n. Let me write one more time so that part also. With that, I'll stop today. Huh? So this is equal to beta power n minus 1 by beta minus 1, which is equal to alpha power n power I plus j minus 1 by alpha power I plus j minus 1. So this part is not equal to 0, but this part equal to 0. So your answer is 0. Why? Alpha power n is how much? N equal to q minus 1. Remember, n is equal to q minus 1. This is equal to 0. This is true for every ij. So every ij, alpha ij is equal to 0. So I proved that. So this is the parity check matrix, right? So I hope you understand the beauty of coding theory. Coding theory is a very high level of mathematics. It is used from linear algebra very frequently, and yeah, right. Okay, I'll stop here.